Okay, so exams have been passed back. Which
Well,
we had some problems with L'Hopital's rule and number 1 and number 4. So we are going to have a related rates problem on the final, but it's a little more, well, it's a lot more straightforward than what is on the test,
go over this question two.
or what was on the test.
Go over this question two. Yeah.
So question 2 was hit or miss. Like some of y'all got it and some of y'all thought that was the graph of the function. That's the graph of the derivative.
Well,
All right, hold on, let me pull it up. All right, so this picture is the derivative, not the function. So when we're doing the first derivative test, we find the first derivative and we set it equal to 0. So where is the derivative equal to 0?
there.
So at -1, oh, let me grab a color.
Maybe. Sure.
This is the derivative. This is not the function. Where is this graph equal to 0? Yep. So this is where the derivative equals 0. Now we would pick test values, plug them into the derivative, and then see if the derivative is positive or negative. So before -4, is the derivative positive or negative? Yep. The values of the derivative before 4 are negative. The values between -4 and -1 of this graph are positive. The values between -1 and 3 are positive. And the values after 3 are negative. So now if we translate this into arrows, negative derivative values means the function is decreasing, increasing, increasing, decreasing. All right, then the follow-up question was, where does this graph have a maximum or a minimum? Like, where does the function have a max or a min? Not where does the derivative have a max or a min? So the function goes from decreasing to increasing at -4. And then it goes from increasing to decreasing at 3. Now, we don't know what the y value on the original function is for those 2 points. So I can only say where the max and the min occur. I can't list an ordered pair. But it really came down to whether you were reading it as the function or as the derivative. If you read it as the function, like the answers were just completely off. So this one ended up being like almost a all or nothing. I had some people do like half and half, which was a little weird. So made this one a bit of a trick question. Like a colleague of mine writes the exam and then I tweak it, and yeah, some of the questions end up being more complicated than I realize. Most of y'all actually did really well on number 1. Like you figured out the equation and you differentiated it. Like the only problem that occurred is it says, how fast does the ladder move up the wall? Blank number of seconds after we start pushing. So that means the ladder starts initially 18 or 19 feet away from the wall, but then we pushed it in a certain number of seconds. So it's no longer at that 18 or 19 feet. It's now 15 feet from the wall. Here, let me yoink a picture and put it up here. So this one is 19 feet and 4 seconds in. So after 4 seconds, when we're pushing at a rate of 1 foot per second, and then since this 1 foot per second is going towards the wall, it's making X shorter. So it's actually negative. So after 4 seconds, my 19 feet becomes 15 feet. And if I use Pythagorean theorem, the y value in the snapshot would be 20 feet. 15, 20, 25 is a Pythagorean triple. So our equation that relates the 3 distances is just our Pythagorean theorem, x squared plus y squared equals z squared. And then when we differentiate that, we get 2x times dx dt plus 2y times dy dt equals 2z dz dt. So our negative 1 foot per second here, that is dx dt. We're pushing the ladder into the wall. That is the x distance being shrunk, changing. So that negative 1 is dx dt. dy dt is what we're solving for. And then dz dt, the length of the ladder. The ladder itself moves, but the length of the ladder is constant. So the length of the ladder never changes. So that is a 0. And then we have an equation here we can solve for dy dt, which ends up being 0.75 or 3/4. And it's positive. So most of y'all got the equation. It was just which numbers you plugged in. If you didn't pay attention to the 4 seconds or 3 seconds, you were plugging in slightly different numbers. You were basically figuring out the rate at which dy dt is changing when we first start pushing the ladder instead of after the number of seconds. I'm going to skip the optimization problem because we don't have one on the final. We do have a related rates, but it's more straightforward. We do have the potential to use L'Hopital's rule, and I had a lot of hit or miss on this. Now, B here ended up being more complicated than I realized. But let's look at A, because A was actually the most straightforward, but some of y'all just avoided it because it had trig. At least that's what I assume was the reason. So if I plug in pi for cosine of pi, pi is a pi number, which means this is a radian number. So this is the cosine of 180 degrees, not the cosine of 3.14 degrees. So you have to make sure your calculator is in radians mode if you're going to use the calculator to do the initial evaluation. So the cosine of pi is -1. So this is -1 plus 1, and then the sine of pi is 0. So we get 0 over 0. This is one of the two indeterminate forms that allows us to use L'Hopital's rule. We either get 0 over 0 or infinity over infinity, but both of those are a fraction. We can't use L'Hopital's rule unless we have this fraction set up. So when I have 0 over 0 like I do here, now I can use L'Hopital's rule. And I take the derivative, not of the fraction. I am not using the quotient rule here. I'm taking the derivative of the top and then the derivative of the bottom, each on their own. I still have my same limit. The derivative of cosine x is negative sine x, plus the derivative of 1 is 0. And then on the bottom, the derivative of sine x is cosine x. Now I plug in pi again. So sine of pi is 0. So I've got 0 on top. Cosine of pi is -1. So I end up with a limit of 0. Now, this natural log one is like several different ways weird. So when we plug in 0 initially, we get 0 squared times the natural log of 0. You can't actually evaluate the natural log at 0. That's why we're approaching 0 from the right. From the right side of 0, natural log approaches negative infinity. So when I have 0 times infinity, I don't know which one's bigger, which one's more important. So we have to rewrite this in a form that we can apply the limit to. So the natural log of x divided by 1 over x squared. So I've like moved x squared into the denominator twice. That's the same as multiplying by x squared. But doing this algebraic step is very weird. When I was adjusting the test, like, I don't know why in my brain this felt reasonable, because when I was looking at the test, I was like, oh, this was horrible. But now when I plug in 0, now I'm going to get negative infinity over infinity. Now I can use L'Hopital's rule. So the natural log of x, I can take the derivative of that. The 1 over x squared, I'm going to rewrite that as x to the negative 2. The limit is still infinity for it, but now I can actually differentiate it. So the derivative of natural log of x is 1 over x. The derivative of x to the negative second is negative 2x to the negative 3. So then that's negative 2 over x to the third. Which I could rewrite that as times x to the third over negative 2. Dividing by a fraction is multiplying by the reciprocal. So now our limit is x squared over negative 2. And when I plug in 0, I get 0. So our indeterminate form was originally 0 times negative infinity, but it became infinity, negative infinity over infinity. But our actual result ended up being 0. So L'Hopital is a very powerful tool, but it doesn't just mean if you get a inconclusive result, you take the derivative. You have to have a fraction. It only works for a fraction. So I had a lot of people just try to take the derivative of this. Some of y'all remembered it was a product, so tried to apply the product rule. Some of y'all just took the derivative of each piece. It just, yeah. All right, so that's the highlight reel from grading the exam. Now, for the final itself, I wrote down a list of problems. Now, we don't have time to do all of these, but I kind of clumped them. Not all of them are perfect analogies for the test, but they're close. So the final exam will be in our normal room, MS 20202. And our final exam is scheduled for Tuesday, a week from today, at 11 a.m. to 12:50 p.m. So a little bit later than our class. So basically 11 to 1. So make sure to eat something before you come in. If you don't normally take caffeine, don't chug a Monster before you come in. That'll just make you really jittery. So the exam is split. There's basically 2 questions from exam 1 content, 2 from exam 2 content, 2 from exam 3 content, and then the last 3 questions are from the new stuff. So one of the questions is going to be that last writing assignment I just assigned y'all. Like literally word for word, that is the last question on the final. The graph is a little bit different. So it's a different function, but it's that writing assignment that's due today. There isn't any web work question that matches that rectangle one in the practice problems. There were some questions in the homework for that section. So you can go back and practice those if you need. I do give you a picture of the graph as well. So if you were doing the writing assignment, like using the graph to draw the rectangles and reason through like where the heights were, like you'll have a picture to work off of for that one. So the first question on the final is going to be about limits, but the format of the question is going to be different than what was on the exam or what is in the practice problems. So question 1 is still the closest to, but in question 1, we get a very disgusting picture. So let me get a picture of the graph. And I say disgusting because this graph has everything going on. All right, and then the question itself is this giant list of limits here. All right, so a lot of these limits are from the left and the right. Not all of them, but some of them. And I clipped off the last one. So the limit as x approaches -4 from the right. So -4 from the right. The function is heading towards -1. All right, now I'm looking at -1 from the left and the right. So -1 from the left, that graph is approaching -2. From the right, the graph is also approaching -2. So since the left and the right are equal, the limit exists. Now note, f of -1 though is +3. Because it's a little point sitting up in a different location. So the limit there exists, even though the function value is different. So what kind of discontinuity is this? Yep, this is a removable discontinuity. The limit exists from the left and the right, but the function value is something different. All right, now we've got our 0 value. So our limit from the left, well, the graph is going down. So that's a negative infinity. And the limit from the right is going up, so that's positive infinity. Let me make that negative a little more obvious. So the limit as x approaches 0, which is it, negative infinity or positive infinity? Doesn't exist. All right, so this is another discontinuity. So strangely enough, this discontinuity is actually a jump discontinuity because the values are different. The values also happen to be negative infinity and positive infinity, but technically an infinite discontinuity is where it like just jumps across an asymptote. So you could also call this an infinite discontinuity. Like I think it might fit the definition for both. So like usually when the limits are approaching infinities, we just call that an infinite discontinuity, whether the infinities are the same or not. Usually we reserve the jump discontinuities for what's going to happen here at 3. So as we're approaching 3 from the left, our function value is -2. 3 from the right, we're approaching -1. So the limit as x approaches 3 does not exist. But that is creating a jump discontinuity because the left and the right are doing different things. Now, when we approach 4, 4 from the left looks like -1.5. And 4 from the right looks like -0.5. So that's another jump discontinuity. And then I think the last limit is 6. Yeah. So 6 from the left is 0.5. All right. So we did a whole lot of thinking, a whole lot of weird stuff with this graph. But this is literally the format from exam 1. So what if you had to do this question backwards? So if I gave you the list on the right, and you had to sketch me a graph. So I'm just putting that thought out there for random reasons. So the assumption is if you understand the concept forwards, you should be able to do the concept backwards. I don't like giving people questions that they have never seen the format on before, despite how horribly I wrote the exams. I know I did that on some of the exam questions. I'm still going to go back and slightly curve some of the exam grades for that. Like I'm gonna add probably like 5 points to everybody's exam 3 grade when I add in the web work points. And I know I was planning on curbing exam 2's grades as well. I still haven't done that. Oh, while I'm thinking about it, the UTSA course survey. I think they're still active. They're in Canvas. They're due today? Okay. So if you do them, you get 1 point added to your final course average. We're going to do it as 5 points on the final, but that's the same as adding 1 point on your final course average. So I'll still probably add it as 5 points on the final exam grade, but yeah. So I won't see those results until after after grades are posted, so you can be as honest as you want for any UTSA course survey at the end of the semester. That's true for all the professors. They're also not like fast food surveys. We don't get in trouble if we don't get all perfect scores. Like I worked fast food. If you didn't get perfect 10s, like your manager got a call and then he came out and yelled at you. And it was just like, dude, I'm sorry. They ordered the most ridiculous burger on the planet and it took more than 5 minutes. Kiss my ass. Like, yeah. So they're not like fast food surveys. So you don't have to give me perfect scores. If you think I did a really good job and you want to give me good scores, please feel free. If there's something, there's also like the number part and then there's the free response part. So you can put whatever you want for the number parts, but on the free response part, it's like, what did your professor do that was really good? What did your professor like do that they could have done better on? So I get to read all of those comments after grades are posted, and I do read them. More than just me reads them. So if a whole bunch of people say that, say good things, like people in the department do hear about it. Or if a whole bunch of people say really bad things, people in the department do hear about it. So we are not above bribery, but the bribery is you just have to do it, not you have to put a certain score. I can get a list of who did the course surveys, and it's just a list of names, not what y'all put. And if there's only like if only 2 people in the course did the course survey, then they won't even give me the results because it's too small of a sample size. Like they'll keep it, they just won't send it to me. I don't think I've ever had a course with that few people fill it out though. That's really only a problem for like upper division or grad courses. So the course surveys are inside Canvas now. They're all digital, so there's no handwriting dilemma. Back when I was in school, which was not that long ago, we were still doing paper, which means like everybody in class had to fill out the paper and the teacher wasn't supposed to be in the room, and then somebody had to go walk the stack of papers up to the office. All right, so we're going to have that first question on graphical limits, and then we're going to have a question on algebraic limits. Now, on the limits now, if it's set up for L'Hopital's rule, you can use L'Hopital's rule, but you have to state which indeterminate form it is. So you have to state if you're getting a 0 over 0 or infinity over infinity. If you've got one of those, then you are free to use L'Hopital's rule now. So before, when we saw this limit, it was like, ew, yuck, I don't like this. All right, so let's see what happens when we plug in the -1. So the bottom, -1 plus 1, we're getting a 0. On top, I've got 7 minus 5 minus 2. I got a 0. We got 0 over 0. So I know before that felt like, oh God, we have to do algebra. Now it's like, ha ha, L'Hopital coming to save the day. Because this is just a polynomial over a polynomial. So what's our derivative of 7x squared? Yep, 14x plus 5. And then the 2 becomes a 0, so we don't have to write it. And on the bottom, the derivative of x is 1. Cool. So now we just plug in -1 and we're done. 14 times -1 plus 5. -14 plus 5 is -9. No factoring required. Now we could still have factored that, and the resulting binomial when we plug in -1 would give us -9.
You have like 3 of those on the other questions.
You'll have 3 different limits on the question. Several of them are open to L'Hopital's rule. At least one of them is not. It's just a limit. You plug in the number and it's a number, and then you're done. And I say it like that because some people get overly trigger happy with L'Hopital and just apply it everywhere. And if you got an answer, you're done. You only have to apply L'Hopital if you get 0 over 0 or infinity over infinity. So there's several limits in the web work. They're all kind of fair game. I was just grabbing a few that I knew L'Hopital would work on. Like our other one here is actually kind of similar to the last one on exam 3, except the fraction already got like, it's not 2 separate fractions. But when I plug in 0 into all this, like I get 0 over 0. So it's like right away, L'Hopital, but I'm going to have a product rule using L'Hopital on this. So it might kind of shoot me in the foot, but on the bottom, that sine 11x will turn into a cosine 11x. So it's going to get rid of my 0 on the bottom. So even though the top derivative is going to be a little messy, the bottom derivative actually works out cleanly. So this should work out for us. So we still have our limit as x approaches 0. So on the top, the derivative of 8x is 8 plus, now we've got a product rule. So derivative of 8x is 8 times cosine x plus, now I keep the 8x times derivative of cosine x is negative sine x. Now I do the derivative of the bottom. Derivative of sine is cosine, but my inside isn't just an x, it's a little bit more than that, so I need a chain rule. What's the derivative of 11x? Yep, just 11. So my derivative of sine of 11x is cosine of 11x times 11. So this is what I think of as like a baby chain rule, because we just get times a constant. This kind of chain rule shows up all over the place when you're doing antiderivatives. So in Cal 2, you're going to have pieces inside the integral that have this kind of baby chain rule all over the place. All right, now we can plug in the 0 again. So I will have the number 8 plus 8 times the cosine of 0. Cosine of 0 is 1 plus 8 times 0 times the negative sine of 0. So this whole thing is just 0. All right, the cosine of 11 times 0 is still the cosine of 0. That is 1. So I actually end up with 8 plus 8 over 11, so I get 16 elevenths. In the past, we actually had to solve this with special trig limits. It was kind of a pain in the butt. All right, what did I pick next? All right. So on first look, problem 13 is like, oh dear God, why? We have a square root of x squared plus 7 is our function. And then it says, use the definition of the derivative. But then at the very bottom, there's this added note. On the final, you do not have to use the definition of the derivative. You can just use your normal derivative rules. Now, I didn't fully read the question, but so the first part, we're just finding the derivative. So you're going to have several questions where they just give you a really nasty function, and you're just going to find the derivative. One of the questions is going to give you an ugly function, and it asks you to find the derivative, and then it asks you to find the equation of the tangent line at a particular value. So you got to plug in the value into the derivative to get the slope of the tangent line, and then find the ordered pair on the function, and then write in the equation. So this one is just practice with the derivative. All right, so the square root, remember, is the same as the 1/2 power. So the x squared plus 7 with the square root is the same as the x squared plus 7 raised to the 1/2 power. So this is outside is just a thing raised to the 1/2 power, and then inside is its own little mess. So we got a chain rule situation. I'm going to do my derivative of the outside, which is just a power rule. Bring the power down, and then subtract 1 from the power. 1/2 minus 1 is negative 1/2. The inside of the chain rule stays the same, and then we multiply by the derivative of the inside. The derivative of the inside is 2x, and then the derivative of 7 is just 0, so it's just 2x. So there's our answer for the first part. The second part, the tangent to the curve is horizontal. So this is asking, where is the derivative 0? So we're going to plug in 0. All right, this 1/2 and the 2 end up canceling, so I have x over the square root of x squared plus 7. So I have this equation, 0 is equal to this fraction. So if I multiply by the square root, I end up with 0 equals x. So at 0, the tangent line is horizontal. Cool. So on the test, it's going to ask for the equation of the tangent line at a particular value. There are some other questions that do that. I thought this one did that, but I was misreading the problem last night. I just finished grading all the exams. I was tired. All right, the next set of problems is just a bunch of funky derivatives. So you're going to have a problem where you get like two functions and they ask for the derivative. I'm a little worried about running out of time. So I'm going to skip 22 and move on to 29.
On Redwood, they has to be. Now I'm using the area terminal, but I don't have to be sure it's using the area terminal. So now we need to know.
Like doing it with a triangle or a circle? No. Yeah, it won't be any of those where it's with an area formula. We did a couple of, like we did one where it was a semicircle and a quarter circle, but no, because those depend on being able to produce the graph of the function. And the one I give you is, it's a weird curve, and I ask for the rectangles the way the last writing assignment was. I don't remember if it was a left hand or a right hand, left side or right side, rectangles. All right, so this question here asks about absolute max and absolute minimum. And it's been a while since we did this. So I'm just gonna look at this problem for reasons. So we are looking at a section of a graph. So we are looking at just this stretch of graph from -3 to 9. So when we look at absolute max and mins, we come up with a list of X values that we're going to test, that are potential overall max or overall min. The endpoints of the interval are always on our list. So I've got -3 and 9 as my potential absolute max and absolute min. The other places that an absolute max or min can occur is if there's a local max or min between that set of numbers. So to figure out where a local max or min is, we have to do the first derivative test. Take the derivative, set it equal to 0. So that means we got to start with our crazy function, which for this one is x to the 7th e to the -x. And we're going to take the derivative of this. So x to the seventh times e to the negative x. This is a product rule. So the derivative of the first one, the derivative of x to the seventh becomes 7x to the sixth times keep e to the negative x the same plus now I keep x to the seventh the same times the derivative of e to the negative x. Well, the derivative of e to the negative x is lazy. It's e to the negative x, but then I get times the derivative of the power. The derivative of negative x is -1. Now we're finding our critical values, so I'm going to set this equal to 0. And I'm going to look for some common things I can factor out. So they both have an x to the sixth, and they both have an e to the negative x. So that leaves me with a 7. This one had a minus sign, so minus x. So x times x to the sixth is x to the seventh, times the e to the negative x, and then the minus sign is there. So I feel like that was a little hand wavy, but that is the factored form of this mess. Now, when we've got a whole bunch of things being multiplied that are equal to 0, I can split the product and set each piece equal to 0. So I have x to the sixth could equal 0. E to the negative x could equal 0. And 7 minus x could equal 0. Well, x to the sixth is only 0 when x is 0. E to the negative x never equals 0. But if you're not sure, I can natural log both sides. And when I try to type in natural log of 0 on the calculator goes, no. So that's when we go, oh, okay, just kidding. That isn't true. There's no values from that. And then the 7 minus x, I add the x over, so I also get 7. So for my table of values, I also need to test 0 and 7. And I double check 0 and 7 are between -3 and 9. So I'm going to check all 4 of these values. Now, unlike our first derivative test, our second derivative test, where we pick test values that are different from the critical values to figure out what the derivative is doing. Here, I don't care what the derivative is doing, if it's increasing or decreasing, whatever. I just care which of these values is the biggest, which of these values is the smallest. Now, in the test, we do still ask about increasing and decreasing. So you do the number line and finish out the process. But for the absolute max and min, we just need to figure out what the function values are on all of these, and then pick whoever the high value is, pick whoever the low value is. So -3 to the seventh, e to the -3. Oh my God. We get -43,927.06. Now the numbers are not going to be this ridiculous on the exam. For this one, we got positive 590.26. All right, we plug in 0. 0 to the 7th times e to the negative 0. Haha, 0. And now let's see what happens with our 7. 7 to the 7th times e to the negative 7. Positive 750.97. So the absolute maximum value is this 750.97. The absolute minimum value is this negative ridiculous number. So 750.97 at x equals 7. Negative 43,927.06, and that occurs at x equals negative 3. Now, WebWork isn't asking us for the x values, they're just asking for the y values. But on the test, you're going to have to do both. All right, problem 44 here is an initial value problem. So we're told the derivative is the negative of 1 over 3 square roots of x. And we're told that the function value at x equals 1 is 0. So they're asking us to figure out what y equals. Like we're trying to find the original function that has this result as its derivative. So I'm going to rewrite this as negative 1/3 times x to the negative 1/2. So I multiply both sides of the equation by dx. I have this setup. dy equals negative 1/3 x to the negative 1/2 dx. Now that it's set up like this, now I can do the integral of both sides. The integral of dy is just y. Now my integral of the negative 1/3 x to the negative 1/2. The negative 1/3 is a constant, so it's going to come outside. And then the x to the negative 1/2, this is our power rule. but we're doing our power rule inside out and backwards because we're doing an antiderivative. So instead of power down and subtract 1, do that process inside out and backwards, add 1 and divide. So the antiderivative of x to the negative 1/2 becomes x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. I still have my negative 1/3 in front. My y equals that. And then because we're doing the indefinite integral, I need a plus c. All right, now before we actually like plug in our value and do more work, let's clean this ugly mess up. So the negative 1/2 plus 1 is positive 1/2. So we're dividing by 1/2. So that's the same as multiplying by 2 over 1. So my function currently is negative 2/3 x to the positive 1/2 plus c. And now I'm going to go back to that initial value. They told me y of 1 equals 0. So this is telling me when I plug in x equals 1, my y value is 0. So I'm going to put 0 for the y. I'm going to put 1 for the x. I'm going to recopy everything else. So 1 to the 1/2, 1 to the any power is 1. So that is 0 equals negative 2/3 plus c. So we're going to have an initial value problem on the test. This is technically from the new section. So this is one of the last 3 problems on the final. Hmm? 44. There's a couple right around 44 that are initial value problems. So the final is 9 questions. 2 from exam 1 material, 2 from exam 2 material, 2 from exam 3 material. So that's 6. And then 3 from the new sections. So one of them is going to be an initial value problem. One of them is going to be a Riemann sum, like the writing assignment that's due today. And then one of them is going to be like number 47. So it's going to have an initial find the antiderivative formula, and then the follow-up is evaluate it with the bounds. All right, so initially, we're going to ignore the bounds. We're just going to do the most general antiderivative. So we have the antiderivative of secant squared. And then our brain goes, yeah, secant squared. What the heck is that again? So We haven't learned any special integration techniques. So when we get weird trig like this and we're doing an antiderivative, this guy is the derivative of one of the trig functions. So we got to remember our trig function derivatives. All right, so we know the derivative of sine is cosine. Derivative of cosine is negative sine. Now we got to remember the other guys. So there's tangent and cotangent. And secant and cosecant. So the way we find the derivative of tangent the long way is we write it as a quotient rule of sine over cosine, and we do the derivative using the quotient rule, low d high minus high d low over square the denominator, and away we go with our cosine and negative sine derivatives. On the bottom, we'll have cosine squared, which dividing by cosine is the same as secant. So the top of the derivative of tangent ends up becoming 1. So our derivative of tangent is secant squared. Our cotangent is a very similar setup, but instead of secant, it's cosecant. And because it's the derivative of a c function, it gets a negative. Now our derivative of secant, like, kind of follows suit. It's related to tangent. Yep, secant tangent or tangent secant. So cosecant follows the pattern. Cotangent cosecant, but it's got a negative on it as well. So now that we remember our derivatives, what is the integral of secant squared of theta d theta? Yep. So all of my derivative rules, if I sketch in my integral on both sides, my integral and derivative cancel out. So I know that the integral of secant squared goes back to tangent. Now, whatever variable I'm dealing with, I keep the same variable. So the secant squared theta, the antiderivative of that is tangent of theta. But then because we're doing an indefinite integral, don't forget the plus c. Now the follow-up is with the definite integral. So the bounds on that definite integral, that is 1/4 of pi, which we could just write as pi over 4. So we've got the bounds from 0 to pi over 4 of secant squared theta d theta. So we've got our indefinite integral tangent. So this is now equal to the function tangent of theta, where theta is being evaluated from 0 to pi over 4. So now to evaluate this, I plug in my top value, so that is the tangent of pi over 4, minus, I plug in the bottom value, the tangent of 0. So this was our fundamental theorem of calculus result, capital F of B minus capital F of A, where capital F was our antiderivative formula. The top value evaluated in there minus the bottom value evaluated in there. Now I put extra parentheses because if your antiderivative formula has any pluses or minuses in there, you're going to need these parentheses. This guy was just a single function formula, So if we forget those green parentheses, it's not going to change our value. But if we had like a polynomial, those parentheses make a big difference. Now the tangent of pi over 4, again, make sure your calculator is in radians mode, and then you can just type this in, and it turns out the tangent of pi over 4 is 1, and the tangent of 0 is 0. So we get a definite integral value of 1. So we're just going to have a pair of functions that do this. You've got to do the indefinite integral, and then you've got to do definite integrals, but the integrals, it's going to be 2 indefinite integrals and then 2 integrals with bounds, but it's the same integrals. So whatever you figure out for the formula on the first part is the formula you're going to use in the second part. So it's not 4 different integrals, it's 2 pairs of the same pairs of integrals. Yeah.
That's like the couple of those total.
Yep. So it'll be 2 indefinite integrals and then 2 integrals with bounds, but it's like the same 2. So like just the way this one was formatted on WebWork, where it had the indefinite and then it had the definite, but it's the same integral.
Yeah.
Yeah.
This is 47 on Woodward.
Yes, this was 47 on WebWork. And there's a couple others around there that you can practice with this. So like 46 and 45, I think. Yeah, I only have 3 minutes left, so it's not really enough time to do another question. If you didn't get to pick up your test today in class, I have a test after a class after this, but then I'm going to be in my office from like 1 to 2. So you can come by and pick up your exam 3. Oh, also on the final exam review, you do not have to do all 50 questions. You just have to get a 70% overall, and that'll be worth the 10 bonus points. So that equates to doing about 35 of the 50 questions. So you don't have to do all of them.